So I just want to point out a little fearful symmetry in the JustReturn code, and that is the fact that we have an add I of -16 to the stack pointer at the beginning to allocate stack space, that is allocation of the stack frame for main, and the add I of +16 at the end to get rid of the stack space. So stack moved down to allocate space for main, stack moved back up to get rid of it. Perfectly balanced as all things should be. And then also we see the manipulation of the frame pointer, the S0. So I would like it if this used the FP instead of the S0, but you're going to have to get used to remembering that S0 could actually be the frame pointer. So we have the store of the existing frame pointer to SP+8. So store off and save the existing frame pointer at the beginning, and upon exit, load up and get the previous saved version of the frame pointer back into the frame pointer register as it's exiting out. And so this is sort of what we call the function prologue. It's just doing standard stuff to allocate space, store frame pointers, and move the frame pointer down. And then the function epilogue is just move the frame pointer back up to where it was, deallocate that stack space, and return back to wherever we came from. Now at this point, I will just make an observation that if we look at the addresses of our assembly, we can see that from the add I to the SD is 2 bytes. So this is address 628, this is address 62A, and that is 2 bytes between them. So there's a lot of these addresses that are only offset by 2 bytes, and having one assembly instruction start 2 bytes after the next assembly instruction is a pretty good hint that there's probably compressed assembly instructions being used behind the scenes. So at this point, we could invoke the awesome chaos magic of Scarlet Witch, but this turns out to have a whole big old rabbit hole worth of stuff that I don't want to deal with right now because that would make this video too long and this lesson too complex. So I'm going to put the complexity of understanding the actual compressed assembly instructions that GCC happened to omit. I'm going to cover that a little bit later and we'll come back to it, but for now instead I'm going to force a recompilation of this assembly, specifically excluding compressed assembly instructions. The way I do that is that I use this -m architecture, march, equals RV64I, which is what I really want, and then D. So I just found that I have to give RV64ID, otherwise it won't compile. It was saying something like, you don't have the D, but it's needed for a calling convention, something like that. So whatever, all I really care is that this is not RV64GC. I don't want the inclusion of the compressed assembly instructions. So if I compile it this way, then I get the exact same code. Add I, SD, add I, LI, etc., etc. So the code is all exactly the same. The only difference is the fact that now every assembly instruction is encoded in its 4-byte form because we have not told the compiler that it's okay to use compressed 2-byte assembly instructions. And with that, I will now actually invoke Scarlet Witch's power. No more aliases. Whoosh. And I go ahead and blow those away. And what I see is that although we still have the SD and the LD, that move assembly instruction just went away. So indeed, it is shocking, it is outrageous. The move is actually just an add I with a register source, register destination, and an immediate of 0. So basically add 0 to your source and move it and store it back into that destination. So there's one little bit of monkey business which I want to call your attention to, because you may have read this assembly and you may have been giving it the side eye and said, hey, couldn't the compiler have just moved 65 directly into A0 instead of moving it into A5 and then moving A5 into A0? That seems very inefficient. That seems very unoptimal. Why would they do that? And yes, they could have done that. They could have moved 65 directly into A0, which is why this is unoptimized code. Yes, we are explicitly telling it to be unoptimized. We are giving the -0, saying set your optimization level to 0, because when we do that, we get nice, simple code that's easy to understand the correspondences back to the high-level language. And indeed, when we tell that to the compiler, unoptimized code generated by compiler is basically a very rote replace some branch of a parsed abstract syntax tree with some specific assembly, Y. So you've got a chunk of the tree, you replace it with assembly. Another chunk of the tree, replace it with assembly. And that leads to unnecessary inclusions, that leads to just inefficient code That's why it's the unoptimized version. It's just simple, rote, and it allows us to see patterns a lot of the times directly between statement 1 in the C source code and, assembly instruction 1, 2, 3, statement 2, assembly instruction 3, 4, 5, and so forth. So anyways, I'm just bringing this up because inevitably, whenever we start out with very unoptimized, explicitly, intentionally unoptimized code, people always ask the question like, why did it do this? And I just want to kind of head you off at the pass for the rest of the class. When you see some weird code that doesn't make sense and you say like, why did it do this? You got to go look and say, did we do it as unoptimized code? And if so, then that's just, the way the compiler heuristics all broke down. It said when I was parsing the code, I just did something very simple, whatever their baseline is, without optimization, and that often leads to weird inefficiencies. Okay, final takeaways from JustReturn optimization level 0. First of all, Xeno hid the compressed instructions from us for some reason. Don't know why yet, but we'll get back to it later. And then also, there's an interesting thing that even when there are no variables, there's no local variables here, there's no saved registers, anything like that, GCC seems to be over-allocating hex 10, 16 bytes worth of space, when the only thing it actually writes to the stack is hex 8, a stack pointer. So we see the add I of -16, that is the allocation of 16 bytes. This adding the 16 back later on, that is the deallocation of 16 bytes. But the only thing it ever stores into the stack is the frame pointer, this S0 register. So it stores a 64-bit, but it allocated 128 bits worth of space, so it's only using half the space. Why did it do that? Well, unfortunately, that's a mystery. And the mystery machine goes rolling by here, and it's going to introduce us to this mystery listery of a variety of mysteries that we will come back to later. So that's the first thing in our mystery list. Why is GCC overallocating space for saved frame pointers? We don't know right now, but we'll come back to it once we learn a little bit more. So in this example, we picked up two new assembly instructions, load dword and store dword. Again, dwords are those 64-bit values. You couldn't possibly have that down in the 32-bit assembly instructions because they have 32-bit registers. And so it wouldn't be making sense for them to load 64-bit values out of memory into registers that are only 32 bits large. And putting our picture back together, we have the introduction of this move, which is just another one of those insidious pseudo instructions. It's just an add I. But we also pop up the store dword and the load dword.